Today we shall start design of slabs. So, we have a few more lectures. So, today we shall start part 1 and this is our lecture number 14, design of slabs part 1. And before we start the design of slabs, let us see what our code says related to your effective span. We have say a masonry wall, this is our ground level, it may be a beam or a slab. We can take as if it is supported by two masonry walls. So, we have different spans, this is your ground level. We have foundation, but we are not interested right now. This may be a beam or a slab. We have, this is your clear span, like clear cover, we can say clear span. And let us say this is the center line of the supports, here this is masonry wall or brick wall. This is called that center to center distance. But this is not the effective span. Our interest here, we have to find out that effective span, like say effective depth, here also we consider that effective span. Where we have to use this effective span? We have to use this effective span to calculate moment. So, we can say for simply supported case, let us say W L square by 8. You may find out the other way also W L by 8. W is the total load or W is the uniformly distributed load. Similarly, we can take say for let us be specific simply supported. We can specify one of the ways, whether we are specifying W UDL or W the total load, whatever way we specify. Similarly, for shear WL by 2 or simply we can write down W by 2, because you will find out in codes either it is written as a total load. Total load is nothing but W, I can say in this case, which is nothing but W times L total load. So, our interest here, what we have to find out, what is the effective span, or in other way what is the that value of L. For this case, if we take this simply supported case, what is the value of L, that effective span, that we have to find out. And let us see that what our code says, IS 456 what our code says. We can take the effective span and we shall get it in clause 22.2 IS 456 2000. In design classes, we most of the time we refer that code, because wherever we have any dispute or other thing, that is the code, it will help us, it will solve that problem. So, if it is simply supported beam or slab, the effective span of a member that is not built integrally with its supports, that means there is no moment developed in the support, shall be taken the lesser of the following two. That means, we are having two, out of that which will be the lesser, that we have to take. So, that means, we have to calculate the clear span plus effective depth of slab or beam, that means whichever the case you are considering. In our case, in next few days we shall design slabs. So, we shall take here slab only. So, clear span plus effective depth of slab or beam. So, that we have to take, that is one case, that is the effective span we shall get. The other one center to center of supports. Out of these two, which one will be minimum that we shall take it as effective span for that problem. So, here if we take say 250 millimeter is the width of the wall, brick wall, then we can find out the center to center distance. If the slab depth say 125 millimeter is the overall depth, so we can calculate, we can assume certain depth, and on the basis of that we can go for calculation of effective span. If it is a 125 millimeter or 150 millimeter, that is the thickness of the slab, then we can calculate effective depth and we can find out the effective span. But if it is continuous beam or slab, so we have, the code says it is in the same clause. If the width of the support is less than 1/12 of the clear span, then it is dependent on the support width. The effective span shall be as per simply supported case, the one which we have already told. So, it will be according to that. That means, it is dependent on the width of the that wall or the support. But it is not, we do not stop it here, there are further clarification. Continuous beam, if it is the other way, for end span with one end fixed and the other continuous. What is continuous? We can start in this way, that means the slab, we are specifying the slab or beam, whatever we specify. If we take it as say simply supported, it can move like this. So, we can go like this, let us say stop it here. Let us say there is a column here, I can put it like this just to make it, there is a column here, a column this side. So, that means I can say this side is fixed. So, our case, in this case we can say for end span with one end fixed, and the other continuous, or for intermediate spans, the effective span shall be the clear span between supports. So, this is the case. So, you will simply take that clear span between supports. So, we can say for this case this is the clear span, and also it is told that for intermediate supports, the intermediate span, these are the intermediate spans, but so we shall take the clear span. What about the other case? For end span with one end free and the other continuous, the effective span shall be the lesser of the following two: clear span plus half the effective width, please note half the effective width, depth, clear span plus half the width of the discontinuous support. That means, here in this case we are talking this problem. So, what should be the effective span, because this side is free, discontinuous support, and we shall get for this case your effective span will be different, and that one will contribute in calculating your moment, shear, other things. That is why it is so important, because if you consider moment, so it becomes a L square. So, obviously, that effective span is a little bit crucial. Okay. Now, we have one more case, continuous beam or slab. In the case of spans with roller or these bearings, the effective spans shall always be the distance between the centers of bearings. So, this is very simple. So, when you are talking say bearings, so then it will be just you take the center to center distance between two bearings. Okay. So, that all of them you will get in the IS 456, but I think this is required to know with examples. Now, what about the cantilever? For cantilever, the effective length of a cantilever shall be taken as 1, its length to the face of the support plus half the effective depth. Please note, in few cases we are taking say effective depth, and few cases we are taking half of the effective depth. So, that you please note. or the length to the center of support where it forms the end of a discontinuous beam. That means, this is a case where it is a discontinuous, sorry, it is the end of a continuous beam. So, when it is continuous beam, that means, here if we take like this problem, it goes. So, in this case what will happen, then we shall take that this portion, we shall take it as say your, we are talking this is as a continuous beam, this is a continuous beam we are considering say, and at the end we are talking say your say slab. So, there we shall take the second case, the length of the center of support where it forms the end of a continuous beam, that we shall take for that problem. So, according to this, that effective span we shall decide which is the case, what is the support condition, and on the basis of that we shall find out the effective span. But what about frames? Because we have to analyze say your problem, we need this one for analysis purpose. If it is a frame structure, that which we can analyze it with some say one say method, different methods by say any program, still nowadays we do it. So, in this case what will happen? In the analysis of a continuous frame, center to center distance shall be used. So, we shall not go or any experiment anything on that effective depth or anything. So, when we shall do the analysis for frames, multi-story frames for say seismic analysis, dead load, live load, different load cases we have to take, and accordingly we have to solve it. In that case, we shall take that effective span, simply the center to center distance. We do that, our code says that moment and shear coefficients for continuous beams, which you can get it in clause 22.5. I think because I always referring these clauses, so that at least you should note down, so that you can refer those clauses. So, where shall we use this? Our code gives few coefficients. So, substantially uniformly distributed loads over 3 or more spans. This is for continuous beams or slabs when we shall take substantially uniform. It is not exactly, but it will be say within 10% or 15%, that way we say. So, and if it is say more than over 3 or more spans which do not differ by more than 50% of the longest, there is a longest span out of that, and if we find that not within more than 15%, then we can use these coefficients. So, one table 12, that simply I have copied that one, that is bending moment coefficients, but we have to use the different coefficients we have to use. So, for span moments and for support moments, there is one span moment and there is support moments. So, near middle of end span for span moment, and we are talking this one say dead load and imposed load fixed, dead load and imposed load fixed. So, loading which are say your chairs if or any machine that is fixed in its position, then we take it as a fixed imposed load. So, in that case near middle of end span, what does it mean? It means so we can take this problem. So, near middle of end span, why near middle of end span? Because the bending moment diagram maybe sometimes it will be say something like that for uniformly distributed load. So, it will go like this, and here it ends, because at this end we do not have any bending moment. So, it will be near middle of, not exactly in the middle. So, it will be near middle of end span, and that one we shall get, and we have to take that 1/12, that coefficient. So, that coefficient, what is that coefficient? It means moment equal to, if we take say total load, so 1/12 W is the total load and L. So, let us write down W total load on that span, which one you are considering, and L effective span. So, M equal to 1/12 WL, here, that is the coefficient we are talking. At middle of intermediate interior span, at middle of interior span, that means this is the interior spans. These are called interior spans. This is called interior span. So, we shall get in the middle of the interior span, here, and that how much we shall get? That is your 1/16 times that WL. Now, what about your supports? At support next to the end support, because we are at the end support there is no moment. So, at support next to the end support, that one will be your minus 1/10 and at other interior supports we shall get minus 1/12. So, here we shall get that you say support next to the end support, and this is your interior support in this particular problem. So, this is your case, we are considering dead load and imposed load fixed. Now, this one, that imposed load not fixed, which is movable, that means today you have at this position. So, you are say you are in the bedroom itself, you can say that you are say dressing table, then you are say cot, and there are so many other things, almirah, all those things you can just move around. So, that way we can say it is not fixed. So, in that case we have to take these coefficients. Okay. Now, what about your other part? There is one, that shear force coefficients. These shear force coefficients here, again the similar fashion, the dead load and imposed load, that is fixed at end support, at support next to the end support, and at all other interior supports. So, we shall get, and we are having that next to the end support we have two positions, one is the outer side, another one in the inner side. What does it mean? It means this is your outer side and this is your inner side, and that V, that one will be equal to say 0.6 W. W is the total load. If it is a simply supported beam, say then W by 2, that is 0.5. Instead of that we are having 0.4, 0.55, 0.5, 0.6 like that, and that we have to take it, that means moment and shear force we shall get it. So, that means if the spans are uniform, that means say almost constant, all the spans same, and load also does not differ much, then we can use the table 12 and table 13. These two tables we can immediately use it, and we can find out the moment and shear force. Now, our code says that for moments at supports where two unequal spans meet, or in case where the spans are not equally loaded, it may be the either case, that means the spans are equal and but loading is different. So, that is why you will get for in one side you will get one moment, considering the other side you will get another moment in the same point, same junction, same support, or if the spans are different, then also we shall get that different moment. In that case our code says that the average of the two values for the negative moment, because we are talking say support, at the support may be taken for design. In that case just simply we shall take the average value, because at each and every level there should not be any confusion or dispute, and that is resolved in these codes. That is why this code is so important. So, this is another clause where a member is built into a masonry wall. We have so far we have taken that masonry wall, that means it is simply supported, but it may happen that your say beam or slab that is integrally, that is in the inserted in the embedded in the masonry wall itself. In that case that certain partial fixity may occur, and our code says where a member is built into a masonry wall which develops only partial restraint, not full, that is not WL square by 12. Okay. The member shall be designed to resist a negative moment at the face of the support, of WL by 24, WL by 24, instead of having say WL by 12, W is the total load here in this case, and L is the effective span. So, WL by 24, that means we are taking half of that. So, partial fixity factor you can say half, that means it is a semi rigid you can say in one sense, or such other restraining moment as may be shown to be applicable, or you can argue okay this is the very determinate problem. So, your partial fixity you know from some other sources or measurement. So, you can take that one also. So, our court says that also you can take, but that should be only taken if the client or the both sides that agree. Beams or slabs over free end supports, where a member is built into a masonry wall which develops only partial restraint, the shear coefficients at the end support, that is which is given in table 13, that is the shear coefficients, may be increased by 0.05. That means, you can add 0.05, that if it is 0.4 then you add 0.45, if it is 0.55 then you add 0.6. So, that way you can take, that is for shear and the other one for moment. Now, let us come to our problem, that so far we know that what is the support condition, what should be the effective span, how to calculate say your bending moment, how to calculate shear force, and that we shall follow. So, but what are the different kinds of slab? If we take, there are, we call it say reinforced concrete solid slabs, mainly we shall take say one way slabs, two way slabs, then flat slabs and flat plates. These are the four different we shall use it. If we say let us say this is one hall, what will happen this one, you will find out that bending, you can take a piece of paper or you can take say your any type of say thin membrane type of thing, if you just a plastic also you can keep it over this type of say arrangement. What you will find out, you will see that it is bending like this. If we make it say almost a square, then we can find out that you will see that both sides, this side as well as this side. Now, depending on this, let us say Lx and this is say Ly, the span in both sides, depending on the situation Ly by Lx, we find out that whether it is one way or two ways. How to design, that means whether we shall consider only one side moment or whether we shall consider the moment both sides. So, in our case one way, if Ly by Lx greater than 2, then we shall take it as say one way. If it is say within less than equal to 2, then we shall take that one. In this problem we shall take two ways. We shall come the other two flat slabs and flat plates, that we shall not design, but that one we shall come later stage, at least I shall show one or two examples how to design that one. Here what happens, we are talking say framed structures. If we take a grid, say like this, say something like this, it is coming. These are all beams, and over that we have the slab. So, these are all slabs and that you have to design. Now, for this problem, if I discontinue the beam here, then we can get, this is one panel, and here we can design it as if that it will bend like this side. So, we have to design that one as a say one way, whereas this one it will bend this way as well as this way. So, we have to design this one as a say two way slab, that I shall show you that in next few classes, that how to design that one. Now, what about your say, but that means it is supported by the beams or maybe walls, whereas it may happen, just to show you that flat slabs, it may happen that it is like this. This is your beam column, sorry. So, this is your, we can design it as a say flat slab. We can also take it as a simply say flat plate, as if it is supported by that columns only. There is no beam, it is just supported over, as if that there are different say prop, there are different supports, and over that you are keeping one plate. Whereas, here you are just making little bit bigger, and then over that you are keeping that slab or plate. So, this is your flat slab, this one we talk is say your flat plate. So, these are the 4 different types of say your slab what we generally design, but in our case we shall only concentrate in this class, that is one-way slab and two-way slabs, which we mainly generally use. The other portion at least we should remember, that is loading on slabs for buildings. Let us say at least we should remember this one, and what our IS 875 1987 that one says. Obviously, we have to take self weight for reinforced concrete, already we have used this one 25 kilonewton per cubic meter. Finishes and partitions, we use finishes and partitions generally at 1.5 kilonewton per square meter. Please note it is cubic meter, and here we are using 1.5 kilonewton per square meter. So, your finish and partition also, then we say partition wall, that one it is distributed, say maybe say 125 millimeter thick say your brick wall. So, you can place it anywhere. So, that we shall distribute that load, and that is your coming that 1.5 kilonewton per square meter. The other one, that imposed loads for roofs, this is 1.5 kilonewton per square meter with access. That means, if we access the roof, if we have access, then we take it 1.5 kilonewton per square meter. If it is not accessible, possibly your halls, possibly that your the roofs are not accessible. So, in that case you have to take say 0.75 kilonewton per square meter. The for floors we are having 2 different one, that if it is a residential buildings, so you take 2 kilonewton per square meter. If it is office floors, then you take 3 kilonewton per square meter. So, we should remember these few, and if it is not mentioned, then we shall assume on the basis of this. That means, if it is office building, if it is not mentioned the load, then we have to take that 3 kilonewton per square meter. What about the concrete cover? That you will find out in table 16. We have already used clear cover, that is 25 millimeter for beam. So, you will find out in table 16 clause 26.4.2 IS 456 2000, and I have just given say mild exposure, because severe there are so many other exposure environmental one. So, nominal concrete cover should not be less than 20 millimeter, it says it should not be less than 20 millimeter. However, for main reinforcement up to 12 millimeter diameter bar, for mild exposure the nominal cover may be reduced by 5 millimeter. That means, if it is a mild exposure and the bar you are using for slabs, if it is less than 12 millimeter or up to 12 millimeter, then we can reduce that 20 millimeter to 15 millimeter. That means, we can use 15 millimeter. So, for slabs we shall use 15 millimeter. If it is not mentioned any other say your environmental condition, any other exposure condition, or any you are using bar within 12 millimeter, then we shall use this 15 millimeter. Okay. The one more part that is very important, because this is the one that which will give you the serviceability. I have already told this is the one that so far whatever I am talking, that is called actually your limit state of collapse. We are talking flexure here for beams as well as for slabs, but there is one more part, that is your say serviceability limit state, so that the users will not feel any discomfort, and that one obviously that your say deflection, that if you have say deflection, that if you say that your slab or the one where you are the supported structure, if it is vibrating too much, if you are having deflecting more, then obviously that you will feel it will be scary. So, at least it should be serviceable, and that one obviously one part, that is your say control of deflection. The even say cracked section, the cracked section, that if you find out cracks, then what will happen, that also it may be scary, but even if you give guarantee, but unfortunately or fortunately, that our assumption is that it is based on cracked section. The design you are doing, that is your actually cracked section design, that is the assumption. So, that means even if you find cracks, then we can say even then it is safe, but the users who are using that one, residents of that building, obviously it may be scary. So, it is a little bit irony also you can say, and that is true for all us also, even if we design. So, anyway, so this control of deflection you will find out in clause 23.2. The final deflection due to all loads, but how shall we find out, because we are not going to calculate that load, sorry, deflection. So, we do it on the basis of something say span. So, the final deflection due to all loads including the effects of temperature, due to temperature also the deflection may occur, creep it occurs, and shrinkage, sorry, this will be R, are measured from the as cast level of the supports. So, from one of the, you can take one say benchmark point, that is the support one of floors or roofs, and all other horizontal members should not normally exceed span by 250. It should not exceed span by 250. That means, if we know span, so effective span say your say 3000. So, you can take say divide by 3000 divided by 250, that you should take it as a your say maximum deflection allowed. The deflection including the effects of temperature, creep and shrinkage occurring, please note, occurring after erection of partitions and the application of finishes. That means, partition or any other that final one and finishes should not, sorry, there is one more mistake. So, normally exceeds span by 350 or 20 millimeter, whichever is less. So, you should remember that span by 350, that is the maximum allowed, that means deflection, or 20 millimeter, that is specified that in no case it should not be more than 20 millimeter. Okay. Now, let us see the vertical deflection limits may generally be assumed to be satisfied, provided that the span to depth ratios are not greater than the values obtained as below. We can satisfy that one in other way, indirect way. We take that certain span to depth ratio, span by depth ratio, L by D. L is the effective span and D effective depth D. So, if we take certain ratio, which we can find out, the code says, if it is cantilever, then our code says, that means here we can get the cantilever, then L by D, we are getting that one say 7, and here this is your basic values of span to effective depth ratios for spans up to 10 meter. That means, if the span is up to 10 meter, then we shall take for cantilever span by depth ratio, that is 7, because it will give us that to choose the, it will also give us to choose the effective depth. In other way, we shall use these values 7, 20 or 26, 7 for cantilever, 20 for simply supported and 26 for continuous beam. So, what we can do, what is the, when you are starting the design, then effective depth I have to find out. So, that we can calculate on the basis of, because I know span or effective span. So, effective span that I know. So, effective span divided by this value, basic value, it will give me to select your say effective depth and also the overall depth, which we can use it for your calculation of load and other things also. So, this one also will help us to take that your say preliminary assumption of your say effective depth as well as overall depth. So, we are getting cantilever 7, simply supported 20, continuous 26. Please note, this is basic values, this is basic values. But one more, that for spans above 10 meter, the basics values may be multiplied by 10 by span. So, if it is more than 10 meters, so 10 by span, so it will be further reduced in meters, except for cantilever, in which case deflection calculation should be made. That means, for cantilever beam or slab, if it is more than 10 meter, then in that case you have to calculate your deflection. Otherwise, we can use that coefficient or that value, we can multiply with that 10 by span, and then we can find out a new value, and that we can use it. So, you have started with some basic value, then we are modifying according to the span, that is 1. We can say that one is your K1. Okay. Now, depending on the area and the stress of steel for tension reinforcement, the basic values, that means the first one that which I have given, or the second one depending on the span by 10 by span, multiplying that one, shall be modified by multiplying with the modification factor obtained as per figure 4. There is one figure, so that we can take it, and that one, what is the case? Area and the stress of steel, that from there we shall find out, and we can further modify the basic value. And let us see that figure 4. So, this is your that figure 4, for different grade, different stress, we can take it, and this is one say service load in Newton per square meter. From there, that is the modification. That means, we can use this figure, and from there, from the percentage of steel, we can modify. Now, how do I know that initially if we start with some say simply supported beam 20. So, here we have to modify the value, but how do I know? That means, it will come from our experiments that what is the percent of steel generally we use for slabs. So, on the basis of that we can find out certain factor, or in other way we have to redesign it. We have to start with basic value, then you do the whole process, again you do it, but that we generally do not do it, because if we are experienced, if we know that one, so then on the very first trial itself we can go. Depending on the area of compression reinforcement, the value of span to depth ratios be further modified by multiplying with the modification factor obtained as per figure 5. There is one more figure in that IS 456, from there we can get another modification. So, this is your that depending on the compression reinforcement. The first one figure 4, that is on the tensile reinforcement, and the other one on the basis of the compression reinforcement. So, our basic value will be modified with the tension reinforcement, also on the basis of compression reinforcement. Now, for flanged beams, the basic values be modified as per figure 6, and the reinforcement potential for use in figure 4 and figure 5 should be based on area of section BFD. Please note, this is BFD that we have to take, and this is your that figure 6. So, for slab design or also for beam design, we have to take all those things, that which I have not given previously, because I thought at least we should concentrate on that formulas that which we are using, say mu equal to 0.138 FCK BD square, like that. And now we are slowly coming to that codes and other things, that how to design it. So, the beam slab design is nothing but you can say a beam design itself. Only thing that in the slab design we take that width of the slab, that is 1000 millimeter. That means, we take 1 meter width, and that is not so. We are doing the same beam design, only thing that here we are taking that 1 meter, and here also that another very simple thing, that we are taking only rectangular one. So, now let us at least start the problem, and which we shall continue in the next class. So, our problem, let us start with one example. So, design of one way slab. Design a simply supported RCC slab for a roof of a hall 3.5 meter into 8 meter, and these are inside dimensions. with 250 millimeter walls all around. So, it is supported by 250 millimeter walls all around. Let us assume a live load of 4 kilonewton per square meter and finish, because there is no partition, finish 1.0 kilonewton square meter. Use concrete M20 and steel Fe 415. So, we have to design of one-way slab, design a simply supported RCC slab for a roof of a hall 3.5 meter into 8 meter, that is the inside dimension. So, clear span here 3.5 meter in one side and another side 8 meter. Since it is one way, so we have to take 3.5 meter with 250 millimeter walls all around. Assume a live load of 4 kilonewton per square meter, though it is quite high, but anyway just for problem sake let us take it, and finish 1 kilonewton per square meter. I have given 1.5, but here we are not using any partition. Use concrete M20 and steel Fe 415. So, this is the problem. So, let us do the first step, that is your calculation of factored loads. Let us take, we shall assume span by D equal to say 25. Simply supported here it is 20, but considering say reinforcement other things we are taking say your say 25. So, we can find out D equal to span by 25, and we have not yet calculated the effective span, because this is after all some preliminary that estimate to find out your loading other things. So, we can take it here directly say 3500, okay, that we are taking this much, and on the basis of that we shall get 140 millimeter. Total depth equal to 140 plus clear cover, let us write down clear cover, plus 5 by 2, I think I should write down here D, D plus clear cover plus 5 by 2, D equal to here 140. Clear cover how much shall we take? Let us take, assume 10 mm dia bar. For slab we shall generally use that 8 mm, 10 mm or 12 mm generally we use. So, in our case we can use the clear cover even for mild exposure we are getting say 15. So, for mild exposure we are getting 15 because we are using less than or equal to 12 millimeter plus, so 10 by 2 and we get 160 millimeter. So, we can now we can calculate the dead load. Now, we can calculate the dead load. Dead load, dead load. So, slab 0.16 times 25 4 kilonewton per square meter, finish 1 kilonewton per square meter which already given, dead load 5 kilonewton per square meter, live load already specified 4 kilonewton per square meter. Okay. So, factored load or we call it say design load. So, we are talking dead load and live load only. So, let us multiply with 1.5 only. So, it comes as equals 13.5 kilonewton per square meter. What about the effective span? So, we know factored load or design load, that is 13.5 kilonewton per square meter. Effective span we have two, let us write down, one 3.5 plus that 0.25, that width of wall 250 millimeter, which comes as 3.75 meter. The other one 3.5 plus effective depth. Effective depth we have computed. Effective depth we have computed 140 millimeter. Effective depth we have computed 140 millimeter. So, we can take it as 0.14 and this comes as 3.64 meter. Therefore, effective span equal to 3.64 meter. Total load for meter width equals 13.5 times, sorry not per meter width, yes, per meter width 13.5 times 3.64, which comes as 49.14 kilonewton. We are talking the total load. So, 3.64 is the span and 13.5 kilonewton per square meter, that is the factored load or design load. So, 13.5 times 3.64, which comes as 49.14 kilonewton. Okay. So, ultimate, now let us calculate ultimate moment and shear, ultimate moment and shear. MU equal to total load times effective span divided by 8 equals 49.14 times 3.64 divided by 8 equals to 22.3587 kilonewton meter. VU, that is equal to W by 2 equals 49.14 divided by 2 equals 24.57 kilonewton. So, this is your MU and the other one is VU. Now, we know what we shall do it. We shall take a beam, a rectangular beam, and we have the width 1000 millimeter. 1000 millimeter is the width, and if we then we shall solve this problem taking that MU and VU. So, we shall find out, and we have to check whether we have and how to provide the reinforcement. So, already we have done that overall depth, already we have computed. So, we have to find out that So, this is 160, little bit higher side. So, we have to check it taking 160 whether it is sufficient, whether it can resist this moment, and we have to provide the reinforcement. So, we have to provide the reinforcement. In this case, what we provide actually, we do not provide the reinforcement the number of bars. These are the reinforcement, this one normal to the paper, say longitudinal reinforcement, but we do not provide it as a number of bars. The one we have done it for say your beams, that say 2 times 2 3 that 20 torr or 320 torr or 316 torr like that, but here what we do, we take it say the diameter of the bar say 10 millimeter torr at the rate of the spacing, we provide the spacing here. So, that we have to find out, that means we have already taken that say overall depth and also we know the effective depth. So, we have to check that taking this moment whether that effective depth is coming less than the computed effective less than the provided effective depth. If it is okay, then we can go for that, we can accept that, and then we have to find out the area of steel. Then we have to check that VU, generally we do not check it, but we shall check for this problem whether the tau V, that shear stress we have computed on the basis of this VU, whether we are getting that one less than the tau C, whether we are getting less than that 0.15% as per the table 19 of IS 456. So, whether it is less than, if it is less than, then we shall not provide any reinforcement, then we do not need any stirrup, and for slabs we do not provide any stirrups, okay, and that we shall continue in the next class. Okay. Thank you.